Okay, second and third laws of thermodynamics. There's a few more concepts that we have to introduce here as well. First of all, the system is the part of the universe that is of your specific interest. And whatever isn't of your specific interest is, of course, the surroundings. The surroundings constitute the rest of the universe outside the system. So generally, chemists just focus upon the immediate surroundings. Correctly predicting the spontaneity of a process requires us to consider entropy changes in both the system and the surroundings. The change in entropy of the surroundings is delta S SURR, and that is directly proportional to the change in enthalpy of the system. It's also inversely proportional to the temperature. So, what you have here is the change in entropy of the surroundings equals minus the change in enthalpy, or heat, in the system, divided by the temperature. So the entropy change in the universe is the sum of the entropy changes in the system and surroundings. The second law of thermodynamics states all spontaneous changes cause an increase in entropy of the universe. Okay? For spontaneous processes, delta S of the universe must be positive. A process with minus delta S of the system can still be spontaneous if, under certain circumstances, in other words, the delta H is for the system is much larger. Okay, so the delta S of the universe is greater than 0 for a spontaneous process. It's less than 0 for a non-spontaneous process. It's spontaneous in the reverse direction, and it equals 0 for a process at equilibrium. The third law of thermodynamics states that the entropy of a pure perfect crystalline substance at 0 degrees Kelvin is 0. 0 Kelvin is called absolute zero. There is no lower temperature than 0 degrees Kelvin. At 0 degrees Kelvin, all molecular movement completely stops. And there's only one possible way to arrange the molecules. We have never, ever reached 0 degrees Kelvin. Standard entropies. It's possible to determine the absolute entropy of a substance. Standard entropies are values for 1 mole of a substance at a pressure of 1 bar and a temperature of 298 degrees Kelvin. In other words, 25 degrees centigrade. Okay? So this is important to remember what these circumstances are. 1 bar, that's 1 atmosphere, and a temperature of 298 degrees Kelvin. In an aqueous species, it's 1 molar concentration. Standard entropy values can be used to calculate standard entropy changes for a process. For example, for carbon, you have the different ones, and notice that this is at 298. That's degrees. That means these are measured at that particular temperature, and this is joules per mole per degree Kelvin. And these are all of the different carbon ones, and you can see the range. You can see the range that you have on these different ones, depending on from graphite to a diamond. You can see the smaller it is, the more ordered it is. Okay, these are gases. Okay, and these are liquids here. So the gases, depending upon how many species, what it is, and what its boiling point is, determines what the entropy is. And you can see that all of these have a greater entropy than those that are liquid, and certainly much more than those that are solids. Likewise with hydrogen, you've got a hydrogen gas with the molecule, and then you have the hydrogen with just a single hydrogen there. The liquids are higher, and then the gases even higher yet. Okay? And then oxygen, we just have one example there. So the calculating delta S is similar to that for the change in the heat that we did way back in the earlier chapters when we were talking about thermochemistry. Delta H was the sum of the heats of formation for the products minus the heats of formation for the reactants. Likewise, the change in entropy is the change in the entropy of the products minus the entropy for the reactants. These are state functions. They only depend upon the final. And this right here should have been this is an F for formation, not for final. Okay. When calculating this, remember to multiply the standard entropies and by formation by the coefficients of the balanced equation, right? So you have to have the balanced equation first, and you have to remember calculating each of those by their coefficients. The second law of thermodynamics can be used to predict spontaneity, but measurements on the surroundings are seldom made. And this really greatly limits the use of the second law of thermodynamics. I don't know why this thing keeps jumping like that. It's convenient to have a thermodynamic function that focuses on just a system and predicts spontaneity. And that is something we call Gibbs free energy change. So the second law of thermodynamics is just this. The Gibbs free energy, and this should be the change, this should be a delta G, not a delta I. The changes in Gibbs free energy, or simply the change in the free energy, allows us to predict spontaneity by focusing on the system only. And so you can see we have the delta H values in here as well as this. And that Gibbs free energy gives us something that we can use in each one. So the sign of delta G indicates if a reaction will be spontaneous or not. If this is less than 0, then the reaction is spontaneous in the forward direction. Remember, this right here is a negative number for an exothermic reaction. If delta G is greater than 0, the reaction is non-spontaneous in the forward direction. With this equals 0, the system's at equilibrium. So you have two different components. This one right here, for exothermic, is a negative. Okay? These are positive values, and they become larger the more disordered the system is. And so it is going to contribute. If it's a more disordered system, this will be a larger negative number. So both of these, if you are contributing to something that is going to be spontaneous, will make it that way. So spontaneous reactions such as those with minus delta generally have the following. A delta H less than 0, that is, as I was saying before, an exothermic reaction. A negative delta H will contribute to a negative delta G. Also, a positive delta S will contribute to a negative delta G. Note that the reaction can still be spontaneous when delta H is positive or delta H is negative, but not both. And notice that there's also this temperature dependence right here as well. So, if this is negative and this is positive, this is going to be a spontaneous reaction because this will be negative. If this is positive and this is negative, this is going to be positive, and so this will be non-spontaneous. Both negative, it depends. Okay? So these this is delta G is less than 0 at any temperature, and the process is spontaneous at any temperature. Here, under these two conditions, it's delta G is greater than 0 and it's non-spontaneous. This process is spontaneous at high temperatures. This process is spontaneous at low temperatures. Okay? So those are the four possibilities. And you can see that these two, for the depends one, it depends upon what the temperature is. And so that just gives you an increase in temperature. And this is spontaneous. Okay? Right here and right here. Okay? These are non-spontaneous up in this region. Only when you get to this region right here are you going to have ones that are going to be spontaneous. And only when you get those that are this high in temperature will these be spontaneous. So the direction of the spontaneity change. To calculate the temperature at which the spontaneity of a reaction changes from spontaneous to non-spontaneous, or non-spontaneous to spontaneous, find the temperature at which delta G equals 0. In other words, T equals delta H over delta S. That is a temperature where delta G equals 0, and by its definition, the system is at equilibrium. Okay? So the standard free energy change is valid under all conditions and will often apply to standard conditions. In other words, delta G equals this right here. Standard conditions are 1 bar and a temperature of 298 degrees Fahrenheit. Also, delta S is usually measured in joules, and this is usually measured in kilojoules. So you have to be very cautious when you're in your calculations, when you're looking at ensuring that both of these are in the right units. Both of them should be in kilojoules, which is what the units that are usually for delta G. So the standard free energy of formation, delta G 0F, for a compound is defined as the free energy change for the formation of 1 mole of a substance from its elements in a standard state at 1 bar and 25 degrees centigrade. Remember, we talked about all of this in Chapter 5. So for this one right here, for example, in this formation, the delta G of formation is minus 237.2 kilojoules per mole. For a chemical reaction of this standard form right here, delta G here is going to be the coefficient of the Gibbs free energy of formation for C plus the coefficient here times the Gibbs free energy for D minus the coefficient here times the Gibbs free energy for A times the coefficient of the B times its Gibbs free energy of formation. So these are the Gibbs free energies of formation of these individual molecules multiplied by their coefficients. And so the general form would be something like this. So these values can be used to calculate then the likelihood of products being formed from a certain set of reactants. This equation only works for calculating delta G of a reaction of a temperature where the values of these are tabulated, so you know how these are formed, and which is at 298 degrees Kelvin, right? Only at that temperature. For any element, its most stable form at standard conditions is defined as 0. Most of our discussions on free energy at this point have involved the standard free energy. All species were 1 bar of partial pressure or 1 molar concentration. There's a general equation that enables you to calculate delta G under other standard conditions. That is delta G plus R times the temperature times the reaction quotient. Okay? The reaction quotient. And this is R is 0.008314 kilojoules per mole times the degrees Kelvin. Thus far in this chapter, we focused heavily on the relationship between free energy change and the spontaneity of a reaction. For a reaction to be spontaneous, delta G must be negative. Another measure of reaction spontaneity is the equilibrium constant. For a reaction to be spontaneous, K must be greater than 1. This should make sense since we've discussed that if K is greater than 1, the reaction will proceed in a forward direction, and the reaction is favored. The reaction of the product is favored.